Similar triangles. The concept of similar triangles is very important. This is because the concept of similar triangles is the basis of trigonometry ratios such as sines, cosines, and tangent. If you want to understand trigonometry correctly, then you must fully understand the concept of similar triangles. We are going to discuss this as easily and as intuitively as possible. Two triangles are similar triangles if all the corresponding angles are respectively equal. As you can see from this picture, triangle in the left is similar to triangle in the right. Even though the two triangles have different sizes, all the corresponding angles are respectively equal. The bigger triangle is constructed from angle alpha, beta, and gamma. The smaller triangles is constructed from angle A, angle B, and angle C. Angle A is corresponding to angle alpha. They have equal measure. Angle B is corresponding to angle beta. They have equal measure. Angle C is corresponding to angle gamma. They have equal measure. Because all the corresponding angles are respectively equal, consequently all ratios of the three pairs of corresponding sides are also equal, and vice versa. Side A in the smaller triangle is corresponding to side X in the bigger triangle. Side B is corresponding to side Y, and side C is corresponding to side Z. As you can see from the first equation, the ratio of side A and side X is equal to the ratio of side B and side Y, and is equal to the ratio of side C and side Z. There is another way to see the ratios of corresponding sides in similar triangles. By rearranging the first equation, we get the second equation. As you can see from the second equation, the ratio of side A and side C in smaller triangle is actually equal to the ratio of side X and side Z in the bigger triangle. That means, as you can see in this picture, the ratio of two sides in the first triangle is proportionally equal to the ratio of the corresponding two sides in the second triangle. This concept is actually very important. This is because this concept is actually the basis of trigonometric ratio such as sine, cosines, and tangent. This concept states that even though the size of the triangle is changed, as long as the measures of all angles are maintained, the ratio of two sides in the first triangle and the ratio of the corresponding two sides in the second triangle are also maintained. That is why we are going to verify whether or not this ratio is valid using Pythagorean theorem. We have provided the proof of Pythagorean theorem in our previous video. Find the link in the monitor. Although this concept is very obvious, you can understand the concept of similar triangles better by observing similar squares and similar rectangles. These two squares are similar squares. Although the two squares are different in size, obviously all the corresponding angles are equal. The ratios of the corresponding sides are also equal. Moreover, the aspect ratio of each square is equal to 1. Automatically, all the squares are similar squares. However, in the case of rectangles, the aspect ratios may vary. Therefore, it is worth noticing. Rectangle A and rectangle B are similar rectangles. Obviously, all the angles of the two rectangles are equal. However, their sizes are different. Even though their sizes are different, Their aspect ratios are kept the same. As you can see from the left equation, the aspect ratios of the bigger rectangles, that is A per B, is equal to the aspect ratio of the smaller rectangles, that is C per D. By arranging the left equation to the right equation, you can understand that the ratios of two corresponding sides are also the same. The first corresponding sides are side A and side C. The second corresponding sides are side B and side D. The ratio between side A and side C is equal to the ratio of side B and side D. So, in two similar rectangles, the aspect ratio and the ratio of the corresponding sides are kept the same. Meanwhile, these two rectangles are not similar rectangles. Their aspect ratios are different, and the ratios of two pairs of corresponding sides are different as well. This is why these two rectangles are not similar rectangles. You can see the same concept in similar triangles. These two triangles are similar triangles. The height of smaller triangle is side D, and the base is side C. The height of the bigger triangle is side H, and the base is side Z. The bigger triangle can be made by prolonging the height of smaller triangle by a factor of p, and at the same time by prolonging the base of the smaller triangle by the same factor of p. In other words, a similar triangle can be made by changing the size of the triangle while keeping its aspect ratio the same. The aspect ratio of a triangle is defined as the ratio between its base and its height. These two triangles are similar triangles. Their aspect ratios are the same. Changing the size of a triangle will not change any of its angles as long as the aspect ratio is not changed. How do we know that changing the size of a triangle will not change any of its angles as long as the aspect ratio are maintained? We will discuss that in the next slides, so stay tuned and subscribe. First of all, by drawing the height on the triangles, the bases are divided into two segments. The base of the smaller triangle, that is side C, is divided into segment E plus segment F. The base of the bigger triangle, that is side Z, is divided into segment M plus segment N. Since side Z is made by multiplying side C with a factor of P, the length of segment M can be measured by multiplying segment E by the same factor of P. Now, let us focus on angle alpha, shown here in the red color. This is the detailed view of angle alpha. There are two similar triangles in this picture. We put the bigger triangle and the smaller triangle in the same spot. That is the point of angle alpha. The base of the smaller triangle is side E and its height is side D. The base of the bigger triangle is side M and its height is side H. The base of the bigger triangle, that is side M, is made by multiplying side E, which is the base of the smaller triangle, with a factor of P. Subsequently, in order to maintain the aspect ratio, the height of the bigger triangle, that is side H, is also made by multiplying side D, which is the height of the smaller triangle, with the same factor of p. As you can see from this diagram, if you multiply the base by a factor of p, but you multiply the height by a factor which is less than p, then you will end with an angle which is less than angle alpha. If you multiply the base by a factor of p, but you multiply the height by a factor which is greater than p, then you will end with an angle which is greater than angle alpha as well. As long as the ratio between the height and the base is maintained, the angle alpha is kept the same also, even though the size of the triangle is changed. From the previous diagram, you can understand that it has been proven that as long as the aspect ratio is maintained, that is the ratio of the base and the height of the triangle, all the angles in similar triangles are maintained and vice versa, even though the size of triangle is changed. By rearranging the equation, as shown in this slide, you can understand that as long as the angle is kept the same, or as long as the aspect ratio is kept the same, the ratio of the corresponding height is equal to the ratio of the corresponding bases. Next, let us discuss about the ratio of the two sides. Those are the ratio of side A and side C in the smaller triangle and the ratio of side X and side Z in the bigger triangle. The question is, are they also maintained as long as the angles are maintained? This is very important because this is actually the basis of trigonometry ratios such as sines, cosines, tangents, and etc. So stay tuned and please subscribe. First, on each triangle, let us draw the height which is perpendicular to the base. By drawing the height on each triangle, the base of each triangle is divided into two segments. The base of the smaller triangle, that is side C, is divided into segment E plus segment F. The base of the bigger triangle, that is side Z, is divided into segment M plus segment N. Next, let us focus on the ratio of the two sides in the larger triangle. That is the ratio of side X and side Z. The base of the bigger triangle, that is side Z, is made by multiplying the base of the smaller triangle by a factor of p. From this, we get equation 1. By using the Pythagorean theorem, side x in the bigger triangle can be expressed in terms of side m and side h, as shown in equation 2. If you want to know how the Pythagorean theorem was proven, click the link in the monitor. Side m in the bigger triangle is made by multiplying side e in the smaller triangle by a factor of p. As previously discussed, in a similar triangle, the aspect ratio must be maintained to preserve the angles. Therefore, the height of the bigger triangle, that is side h, must be equal to the height of the smaller triangle, that is side d, multiplied by the same factor of p. Therefore, equation 2 can be simplified into equation 3, as you can see in this slide. Moreover, by eliminating the factor of p, equation 3 can be simplified into equation 4. Next, let us focus on the left hand of the equation. The root square of the square of g plus the square of d is actually equal to the side A in the smaller triangle. Therefore, equation 4 can be simplified into equation 5. From this equation, you can understand that the fact that in similar triangles, the ratio of two sides in the first triangle and the ratio of two sides in the second triangle are equal as long as the included angle is maintained has been proven. This is the basic of trigonometry. By rearranging equation 5 on the left to the right equation, you can also understand that the fact that in similar triangles, the ratio of the two pairs of corresponding sides are equal, as long as the included angles is maintained, has been proven. Conclusion. A pair of triangles are similar triangles when one of the following three criteria is fulfilled. One criterion is sufficient. Criterion number 1. Three angles in the first triangle are respectively equal to the three angles in the second triangle. Because the total of angles in triangles is 180 degrees, then this criterion can be simplified into the following. If two angles in the first triangle are respectively equal to the corresponding two angles in the second triangle, then the two triangles are similar triangles. If this criterion is fulfilled, then you don't have to consider other criteria such as the ratio of corresponding sides. If you want to know the proof of the total angles in a triangle, click the link in the monitor. Criterion number 2. If the ratios of the three pairs of corresponding sides in two triangles are equal, then the two triangles are similar triangles. If this criterion is fulfilled, there are no need considering other criteria. Criterion number 3. As you can see from the figure, if the ratio of two sides in the first triangle is proportionally equal to that of the second triangle, and if the included angles are equal, then the two triangles are similar triangles. This criteria has been proven in this video. Moreover, this criteria is the basis of trigonometry ratio, such as sine, cosine, and tangent. You can donate through Patreon and PayPal. Don't forget to subscribe.